Hello people, this is part 2 video of a topic where we discuss a graph attention network. In this part we will discuss how to implement multi-head attention mechanism. So the main idea behind multi-head case is that you create, say, k different representation of input data, and from these different interpretations you construct basically new ways for message passing. That's the main idea. So since we need k different interpretations, original input data stays the same. I gave actually some thought why we pack feature vectors as rows. It's just very common in this field and similar fields when we pass basically you can consider them as rows, but again I guess the idea is that we just have some object of dimension d, and basically we want to map it to some d prime via linear transformation, right? And usually what you're taught in linear algebra, that you do matrix multiplications basically as columns, some column, a matrix column, right? It will be y, some a, x, but that's not how it's done usually in this field, right? Basically we just want to transform d to d prime, and we need the matrix that's d times d prime, so we can basically batch transform, and of course it corresponds to actually left matrix multiply. Because of the dimensions. It's kind of against the general convention, but I think it's quite curious. Okay, so we need to calculate k different interpretations. In this case, we need k different projections. And as we've discussed in previous part, we can do it by stacking k different transformation matrices on top of each other. And actually, that's what I show here. I use linear layer that maps from n features to k different heads. Here I don't change the dimensions, but of course you can. And for test, I fill first matrix a scale of 2, second matrix is transformation scale of 4, and then I perform individual operations and compare it with if I apply the concatenated version, and that's what we get. Original H matrix, transformations, the result of individual transformations, and this batched / concatenated version, it produces the same result, except that it produces a two-dimensional matrix, and probably we want to separate each head into its own dimension, and that's what we do. So dimension 1 will separate the heads. And the structure that we get, we view this G matrix as basically a storage for each node. And in this case, you see the first component, say for a first node, it stores actually not a vector, but a matrix. In this matrix, first entry represents head 1, second entry represents head 2. And this will be the general theme of this multi-head attention idea, that we get additional dimension that we have to deal with. So then we have to construct basically pairwise concatenations of features of nodes. And we can follow the same procedure as we did with the case of one head. Basically, we get this flattened representation. Again, because we couldn't concatenate it in some kind of broadcastable way, we have to actually generate all the elements, all the pair of elements, and then concatenate in the feature dimension. And basically, that's again the structure that we want to get, some left and right part, but in our case, we want to actually introduce additional dimension of n heads. And if we see that our storage basically is this shape, and we think, okay, how we can construct this left and right parts from this storage, again, we basically repeat everything we did before, except I don't remember which dimension we did it prior. I think the same dimension, but again, we want to do repeats in a row. Well, in the 0 dimension, we want to repeat rows in this case. And this is the test, the example. I do repeats and 2 times, and then I concatenate it into one big matrix, and I concatenate it on the feature dimension as we're supposed to. I can show, of course, only a slice of this data because it's actually 3-dimensional. And that's what we observe. It's basically the same results when we had one head, except now I'm slicing, showing only the slice, right? And then we reshape it back to shape that's more like an adjacency matrix. And again, we know that each entry in this n by n matrix is just some vector that will represent interaction of node I and node j. But again, there are 2 interpretations for this. Whatever it is. Here's just a brief look, okay, how it looks like. Actually, it's not probably correct. Oh, okay, I checked two different nodes. So 1, 2, and 2, 3, and 0, 1, okay, you get it. And of course, these are the different representation of node 1 and node 2 for one head, 0, 2, 4, 6, 0, 1, 2, 3. And this is what you get, the concatenated versions. Okay, next big thing that we have to calculate projections onto attention vector. You can view this action like you basically want to find how similar. Well, it's actually called the similarity of 2 vectors. Maybe you can view it as a projection if this concatenated version is aligned with our parameter A, it will produce a large weight. If it's orthogonal, then 0 weight may produce negative weights. And how we can do it, in case that we have additional dimension, we actually cannot use one single linear layer. That would be just a simple matrix multiplication. We can actually apply only one vector to each, basically concatenated head, whatever. That's what they do in the resource that I've linked on top. I'm not sure why, and that's why excuse me, and that's why I have implemented like these k different vectors, and actually I have to do basically element wise dot product. Basically that's what it will be, and I want to store this a vectors as columns. We know that this interaction between I and ith node and its neighbor, some neighbor n, is this matrix where rows are concatenated vectors. And basically we want to do some kind of dot product that diffuses inside, basically like some sort of element-wise operation. And actually when we defined how it will work with this storage that we either actually use currently or we can freely choose, like how we pack A, I've decided to pack A such that this multiplication will actually look like matrix multiplication of row and column, but it can be different. And we just observe some ith element, I don't know, element 1, and write summation for it. And it looks like typical summation of, second index for rows times element in columns. And actually for arbitrary kth head, we have this expression. And if we take a look at the indices of this operation, we can write an Einstein sum. Although we should remember that we've only made this substitution, that we explore only interaction between ith node and its neighbor, right? Actually, we want to broadcast it for all interaction. And we enforce this broadcasting just by adding additional indices on matrix C, and then of course we should add it on the result to match dimensions. And that's how I do it. I actually construct dummy vectors and produce this summation for all the entries. And that's dummy vectors again, as previously. In this case, it will produce a summation. The second vector is summation multiplied by 2. And if we take a look at the interaction of node with itself, node 0, we see that first concatenated feature representation will sum up to 2 and second to 8. So it works. In a sense, you can repeat it without Einstein summation, but if you observe this expression, you will notice that it's very closely resembles like typical matrix multiplication for, in this case, for entry kj, except in our case we know that we only need matching less dimensions, k and k. J should be equal to k, and that's basically saying if we can compute this full multiplication, and then we just extract the diagonal kk element. And actually we again broadcasted, but in this case of matrix multiplication, it will broadcast itself. But about the diagonal, because it's a tensor of rank 4, we actually have to specify that we only want to take a diagonal on the internal matrix. So interaction of ith node and its neighbor is represented by a matrix, and when we want to actually take diagonal of this inside matrix, which would be like previous to last and last dimension, or you can write it in index -2 and -1. Here I show you this one-liner, or even maybe simpler, you can just pretty much mimic the dot product. You just cross multiply everything, every element with according element. again, it will broadcast itself automatically. And then to actually do a dot product to finish, you just sum over this last dimension. Again, it's pretty simple, and also kind of one-liner. And of course, all the approaches yield the same result. Again, probably computing interaction between every node and each neighbor. Again, we do it, but maybe we don't want to actually use all the weights. So we mask only those weights that are actually present on the as connections. In this case, I add extra dimension, so the third dimension of heads will be broadcasted. Row normalization, again, since each row of this matrix with weights will sum up the neighbors of some node, we want weights to sum up to 1. And in this case, it's dimension 1. Similar to its previous case, although we have added additional dimension in the end, we should remember that the first index represent node which we are interested in, second row represent neighbors which we sum up, and actually we want to apply the softmax across this neighbor dimension, and the k dimension stays unaffected. So this is the simple example, pretty much the same activation layer. Feature aggregation is kind of tricky. We should call back, remember how we did it in the case of one head. So in that case, we had aggregation via dot product of rows of G, and for node 1, we just took row 1 of this adjacency matrix or attention matrix, and we have to repeat it in the same fashion here, although we get extra dimension. So you've noticed I've kind of introduced indices that are not just MNL or AJK, whatever. I wanted to encode actually the meaning of each dimension in here, so we can actually follow and have some intuition why we do these operations. So in this case, I should add prime here. So in this case, first dimension of G prime is a storage that holds features of each node. So each eth entry represents some features of eth node, and second dimension holds heads. Similarly with the regular G, except that here we can view first index as its neighbor of some node of interest I, right? So it's kind of not the same in the view of what we want to do during aggregation. And of course, the adjacency matrix. So the first row I represents the neighbors of ith node, and the second dimension is weight of each node for node of interest I. So basically, if you just look at these indices and we understand which dimension is needed for which of other metrics, we basically can write a summation rule just by matching these dimensions. So how do we get basically indices AKF from ANK and NKF, right? We just know that we have to do an aggregation, a sum over neighbors. That's pretty much what you can write without even delving deep into this. Alternatively, of course, if you you will still have to check if it's correct. So basically, you can examine one case. Again, similar to one head case, you just examine first entry of G and take coefficients of weights basically from the first row of A. And that's basically the structure that we have. Again, first entry now is a matrix. Again, other entry again is a matrix. And you can write all the indices here. And you can observe that you have to calculate that dot product between two columns. Left columns with left columns and so on. And you just write one particular solution and consider that you can do it basically for any row of A and for any head. Well, it's kind of our interpretation where when we sum up individual G's. So, but in fact, we have to write, when we write Einstein summation, we have to write it for the element. And of course, we understand that each entry of G is some element. All the entries in this vector G are just elements in a bigger matrix, bigger storage matrix. And that's what we do here. We express each entry of this vector G. And if we look at the summation, we get exactly the same result we came up before. We do a test. It's kind of messy here, but it boils down as if we have defined these storages as so, it boils down to that we want to examine what is the aggregation of zeroth entry. We get to use zeroth row and all the storage of all the features. And in this case, I create two different adjacency matrices. But when these are just the slices, where is the oh, here it is. So it's actually slicing the last dimension of heads, right? But actually, when you extract, in a sense, a row, it will be two-dimensional matrix with first row being the weights for head 1 and the other and the other head is actually a row column 2, I'm sorry. And what we want to get is to basically what you get during this operation is just the summation of entries of G, where each row represents our feature vector with weights from columns of this zeroth entry. Well, you get it. In this case, we want to get a weight of node 0 as 0, 1, and 1, and that's what we get. We don't take any G0. We take through 2 plus 3 and 3 plus 5, and that we get as a row 1, and we repeat this with the second rows, but with different weights. And that's what you get. And that's pretty much it. That actually means the result will be, what will it be, like k different rows which represent k different aggregated features, new features, k different variants for each node, well, of length f prime. And what you can do with these different interpretations is you can, like, the simplest way is just to take a mean across all the individual feature. That way you will preserve the structure. Or you can actually concatenate it if you want to actually examine it simultaneously, if you will. So now I will go through the maybe very fast through the just one dummy case where I've gathered everything into one sequence, basically continuous output with this dummy matrices. First we do two different interpretations. Then when we reshape it, then we concatenate features for different heads. Then we apply a dot product, element-wise, if you will, masking, and basically aggregation, and produce either concatenate version or mean across the feature dimension. And then we can view, actually I've implemented the test case from original paper using Cora citation network. There's some description. It's not actually correct. I'm not sure why, but generally it represents that our nodes represent each graph, and the features that each node holds represent some kind of collection of words. Like first, it's a dictionary of 1400 words, and basically if this word is in this publication, it will just mark it the eth word with 0 or 1, right? I import this dataset via torch geometric because it will do most things for me. Maybe one caveat is that you get test, validation, and training subsets, and we will do semi-supervised learning. That's why I have to actually combine some of these or split apart. So since our memories are still fresh, let's go through the graph attention module, like layer, and we pass the original feature of nodes, and then specific for a network number of heads, this f prime dimension after first transformation, the dimension of features. We can change the nonlinearity. We can, well, this is optional whether we want to mask or we don't. Actually, we want to mask. I've tried and it doesn't converge simply. There are simply too many options. Different parameters, and in this case we have k different projections. Attention vectors defined as parameters, again as a matrix of size, concatenated times n heads, activations, whatnot. The forward pretty much the same, k different projections, calculate concatenations, and then we apply dot product with attention vector, perform masking, softmax dropout, and then we do aggregation via Einstein summation. And the last part, well, in the paper they use two-layer graph attention network, and each layer ends with a different action. So it can be, in this case, we are activating independently or all the heads, and then actually we do concatenation, or alternatively we can take a mean and then do activation. The basic structure that I've extracted from this paper. Where was it? So there is some information. Okay, I won't search it, but basically you can write it. You can find it in just text. How they did it. First layers was 8 heads, number of hidden dimensions 8, activations, concatenations. So in this layer they concatenate all the features, and layer 2 acts as a classification part when actually they have only one head, and the result is a vector of size of number of classes. They apply regularization. I don't use it, and they drop out. And the network is as follows: basically 2 attention networks, spike, basically dropouts all over the place, even on the input, which is curious. So how do I prepare the input data? In this phase, we have to find the adjacency matrices. We will have 2 different subsets, one for training and one for validation. That actually means that we have to cut the graph, the one big graph, into 2 parts. And actually, since this torch geometric planetoid allows you to specify how many tests or validation, it will just produce a mask that basically shows which nodes will be in which subclass. But in this case, we create the big graph from all the nodes, all the edges connections specified. There's one like small problem or caveat. If you think about it, if we split a graph, maybe we will split it over edge which is the only edge that connects 2 nodes. That means that 2 nodes will remain without the neighbors, and that's very problematic, since we cannot. You can view it as a at some point some row of adjacency matrix will have only zeros, and then you will try to normalize it. It will break, right? So in a sense, maybe you want to just remove all the nodes with so-called degree 1. That means, or degree 0. I guess degree 0. That means that nodes which don't have connections after the graph were split. Or alternatively, you can actually add self loops. That means that even if a node will be split, it will still keep its connections. And actually, these self loops, they are really important. Without them, actually, I think the network doesn't train. And even though it may be weakly interpretable, like in terms, if we try to find an example in the real world, we usually don't consider that something interacts with itself. But I guess good interpretation is to say, if your primary goal is to perform an aggregation, you don't want your neighbors to fully define yourself. You want to keep some information on yourself, or you can view it as you are yourself and you just do some modification of this representation based on your neighbors. I guess that's good interpretation. But again, I split the main graph into 2 parts, where I just use masking from planetoid class, basically, which is separated into training and validation sets. I have to sort them because I don't know why. Oh, I remember why. Because these masks are for, in a sense, for original nodes that are in specific order. And then when I create subgraphs, it will shuffle and I cannot apply the mask to this data. I just do some tests so I can view that actually I've split everything correctly. And the main goal is I extract adjacency metrics from training and validation sets. And then I do one hot encoding of clusters and do a training loop. I don't use evaluation here, but in general, the goal is to do a semi-supervised learning. What it means that I supply only a fraction of data, and I can change at random which nodes I compare to original. In this case, authors presented, they thought that I should basically take 20 nodes from each class and then do comparison only on them. So I generate a mask. Actually, I think this approach is kind of bad. I'm not sure if it works. But right, I only use a mask subset, and then every once in a while I check the accuracy on the training, on the validation data. And the training loss just jumps around. Test accuracy is for validation. It somewhat reaches 70%. Authors claim that they have accuracy of 83 or whatnot. I'm not sure. Again, maybe my masking is not correct, and maybe I should have added regularization, or I should have made more iterations, but it kind of looks like it's saturating. And well, you can view some portion of data or all the data as a projection on 2D space using a TSNE algorithm. And you see it kind of separated the validation set. It's all over the place, but I think it's a good test case. Just to follow through this case and maybe learn something. Actually, I've somewhat enjoyed the process of deciding how to actually approach this additional dimension of heads, and I hope you will learn something from it. But yeah, that's it. Thank you for watching.